problem. So limits and vacation request. Which numbers will solve my Sudoku? And given factory capacity, how much of product X versus product Y should I make to maximize profit? And then what weight values will minimize the loss function of my neural network? So these are all search algorithms. These are all problems begging for a search algorithm. Gradient descent in itself is a search algorithm because you're trying to find the right parameters to fit a model to. So the most naive way you can try to solve these problems is using an iterative brute force technique, right? But this is not going to be practical for a number of reasons. The primary reason is it's going to take forever. You're never going to, it could theoretically take forever to just infinitely generate random combinations, and you're unlikely to solve the problem unless the problem is really small and really trivial. Doing random brute force is effectively going to take forever. So we're going to need some more clever techniques. To get around this and to find shortcuts that bring us closer to the solution. And this is where heuristics and metaheuristics comes in. So metaheuristics, they are a powerful tool to find a solution to an optimization problem. They're really flexible. Depending on how ambitious you are, they're relatively easy to code from scratch. We'll see that today. And these algorithms, they leverage controlled randomness, which we call stochastic programming. And a heuristic is a clever strategy to guide a search algorithm to a more likely solution. So a heuristic is a rule of thumb. It's a rule of thumb that we employ. It's a bias we put in the algorithm to try to grab it. While the algorithm is going to be random based, it's going to bias that randomness towards what we think the solution is more likely to be. So, for example, if we're trying to maximize revenue with limited factory capacity, we want to prefer high-value items first in our search. And more general, and we'll see many examples of heuristics today, but more generally, heuristics will start searches where a solution is more likely, and it'll deprioritize less likely solutions. So I always like to go back to that example. It's like, well, if we're trying to maximize revenue with limited factory capacity, well, I want to look at the most high-value items first. We'll talk about that more later today. And so metaheuristics, what they do is they will apply a variety of heuristics, essentially using a heuristic that manages heuristics. Now, this sounds really complicated, but when I show you an example, you'll probably realize this isn't so bad. Now, gradient descent in itself is a heuristic or a metaheuristic. So because you're using the slopes, the derivatives, the differentials of the parameters and taking a fraction of them and then adding them to those variables, those parameters, to lead you towards a solution. So gradient descent is a heuristic, is a metaheuristic. And I don't think most people are aware of this whole taxonomy that gradient descent belongs to. It belongs to this whole family of algorithms. And like I said earlier, when you learn when you become aware of this family of algorithms, you start to appreciate the area of optimization and the problems it can solve. And that way, you're not another person who gets approached by a vendor who sells you an AI, and you think, oh, I must be using machine learning and gradient descent. No, they're using simulated annealing. They might even be using linear programming. And I have seen this happen many, many times. I mean, you just take an algorithm, an optimization algorithm, call it AI, and you can charge 5 times more for it. And I have seen this done in practice many times in my career. So, the traveling salesman problem. This is fascinating. And some of you might have heard of this problem before, some of you might have not. but I think that there's a lot to appreciate here. So the traveling salesman problem, it's one of the most elusive and studied computer science problems since the 1950s. Now, it also serves as a benchmark for transportation and routing problems, and just the capabilities of computer science altogether. The objective is very simple. Find the shortest round-trip tour across several geographic points or cities. Easy enough, right? You have all these points. You have all these locations you want to visit. Find the shortest round-trip tour to visit all of those cities. That's actually a very practical problem to solve because there are a lot of things that we have to optimize the routings to. Even for things like circuit boards, the traveling salesman applies. So as somebody who's done circuit board development and everything, like here, let me see if I have it. Here's an Arduino chip, or an Arduino board right here. What has to happen on circuit boards, you have to make all of these connections across all of these different components so that the electric signals are carried around in the most effective, shortest tours possible. So the traveling salesman problem actually does apply to many surprising areas, including circuit board developments. And you'll find a lot of algorithms and circuit board designing software use these techniques I'm going to show you today. So again, pulling back, the shortest round trip. So the traveling sales problem was to find the shortest round trip tour to visit several points and cities. Here is what makes it so hard. Just 60 cities is going to give you 10 to the 81st possible tours combinations. Now, to put in perspective, that is more tour combinations than there are observable atoms in the universe. Now, this is what I find fascinating about optimization is that you have a relatively simple problem to define. The solution is astronomical, though. And we'll see an example of this later where if you're trying to schedule classes in a classroom, that you can reach astronomical combinations of numbers that you're dealing with. And it's very satisfying to be able to still solve the problem with an effective approximation. Now, let's learn the first metaheuristic to solve this, hill climbing. So you're going to start with a random solution, even if it is poor quality. And you're going to repeat the following steps for a number of iterations until the solution cannot improve anymore. You're going to select a random part of the solution and change it. If that results in an improvement, you keep it. Easy enough. And this is a very foundational algorithm and one that things like gradient descent are based off of a lot of the ideas that this presents. So again, it's very simple. You just repeatedly change the solution, random parts of a solution. If those changes results improvements, you keep it. Otherwise, you revert it back. So let me show something right here. I'm going to do a few demonstrations. And I want to do it in the shortest round trip tour possible. So the most naive way you can approach this is you can just start at a random point and then jump to the next closest point, to the next closest point, the next closest point. The problem is, and if you look at this closely, you'll see that we don't end up with a good solution. You'll see that we got some overlaps and we got some questionable connections. And so while that heuristic of just jumping to the next closest point, the next closest point, next closest point makes sense, you'll notice that for larger, more complex problems, it starts to fail badly because the moment you start having overlaps in your itinerary, you don't have a good solution. So another algorithm that you can try is the hill climbing one that I just mentioned. So here with the hill climbing, what I'm going to do, and watch very closely, is you'll start with a random itinerary, even though it's poor, even though it's It's a sucky itinerary. But then I'm going to take 2 random edges at a time and randomly swap them. If that results in an improvement, I'm going to keep it. Otherwise, I'll revert it back. I'm only animating the improving changes. And you'll see right here that as soon as it's done, I don't have any overlaps. And I get a distance of 16,133 kilometers. So that is fantastic. So that is really, really good. So that's really good. So that is hill climbing. You just start with a random itinerary, and I'll play it again just because it's satisfying to watch and just to emphasize my explanation. You start with that random itinerary. You make random swaps of 2 edges at a time, and if that results in improvement, you keep it. And you'll see by the time it finishes, we have no overlaps, and then everything looks fantastic. There is one complication here, though. So let me ask you folks this, and feel free to post the answer in the chats. What is keeping me from getting to a better solution? What do you think that is? What is keeping me from getting to a better solution? What do you think? What would keep me from getting to a better solution with even less distance? Anybody? What would keep me from getting to a better configuration? So TT is saying randomness, and this is a very good point. Yes, randomness is inevitable. And you'll find that even with stochastic gradient descent, which uses the word stochastic, therefore it's random, you'll find that you'll get a different answer every time you run it. And just like this is random base, you're going to get a different answer every time you run it. I'm going to tell you right now that as you go into the world of optimization and AI and machine learning, randomness is just part of that domain, for better or worse. Now, funny story. When I used to work for